Good evening. Welcome to Sleepy Science Drift, where the mysteries of the cosmos unfold in whispers rather than shouts. Tonight, we turn our attention to something that arrived quietly, moved through our neighborhood without fanfare, and will soon depart forever. Its name is 3I/Atlas, and it carries a designation that did not exist in our astronomical lexbooks until very recently. The letter I stands for interstellar. The number 3 tells us it is only the third confirmed visitor from beyond our sun's family that we have ever recorded. Think about that for a moment. 3. In all of human history, with all our telescopes and all our watching, we have confirmed just 3 objects that were born around other stars and wandered into our view. What does a traveller from another star system leave behind when it passes by only once? That is the question we will hold softly tonight, turning it over like a smooth stone in the palm of the mind. Some questions do not demand immediate answers. They ask instead for patience, for attention, for a willingness to sit with uncertainty and see what shapes emerge from the darkness. This is one of those questions. Before 2017, the category of interstellar objects did not officially exist. We had comets, familiar wanderers on long elliptical loops that returned again and again. We had asteroids, rocky fragments that never strayed far from their ordained paths. Everything we observed belonged to the sun's extended family, bound by gravity into predictable rhythms. Then something arrived that refused to fit the old categories. Its path was wrong. The mathematics showed clearly that it would never return. It was passing through, a stranger at the door. And after that moment, the International Astronomical Union quietly added a new label to the catalogue, I, for interstellar. A single character that carries enormous weight. Now we have 3 confirmed entries in this new ledger. 1I ʻOumuamua, which arrived first and left us puzzling over its strange tumbling motion and lack of visible coma. 2I Borisov, which behaved much like the comets we know, trailing gas and dust in a reassuring display of familiarity. And now 3I Atlas, discovered in early July of 2025, moving on a steeply tilted path that cuts across the orderly lanes of planetary traffic, like a cyclist gliding the wrong way down a one-way street. What if these visitors are more common than we have been told? What if the space between stars is not empty, but quietly populated with fragments from countless other planetary systems, each one drifting on its own long journey? 3 confirmed objects in less than a decade suggests we are only beginning to glimpse a much larger population. As our instruments improve, as our surveys sweep wider and deeper, we may find that the galaxy is full of these quiet wanderers, and that our solar system sits in the middle of a slow, invisible rain of material from elsewhere. Tonight, we will move through the story of 3I/Atlas without hurry. We will examine how we know it is truly from elsewhere, how we find such faint objects in the vastness of space, and what its dim light reveals when measured with patience. There is no alarm here, no call to panic, just numbers, observations, and the slow assembly of understanding. If calm science before sleep brings you ease, then settle in. Let the details wash over you like a gentle tide. Some will stick, some will drift past, and that is perfectly fine. The invitation is simply to wonder, softly, at what crosses our sky unannounced. The geometry of escape is where certainty lives. In astronomy, we do not often get to speak with absolute confidence, but orbital mechanics offers one of those rare moments. When an object moves through space under the influence of gravity, its path is determined by 2 things, its speed and its distance from the massive body pulling on it. Add these together in the right way, and you get a number called the total energy. If that number is negative, the object is trapped. It moves in a closed loop, an ellipse that repeats endlessly. If that number is exactly 0, the object sits on the knife edge of escape, tracing a parabola that never quite falls back, but never quite breaks free either. And if that number is positive, the object has more than enough energy to climb out of the gravitational well and keep going forever. Its path becomes a hyperbola, an open curve that arrives from infinity and returns to infinity. The shape of that curve is described by a value called eccentricity. A perfect circle has an eccentricity of 0. Any ellipse that closes has a value between 0 and 1. A parabola, that exact threshold of escape, has an eccentricity of exactly 1. And a hyperbola, the signature of an unbound traveller, has an eccentricity greater than 1. This is not opinion, this is not interpretation, this is geometry, as certain as the fact that 2 + 2 = 4. When astronomers fit observations of 3i Atlas to the equations of motion, and the solution demands an eccentricity comfortably above 1, the sky has written its verdict in a language that does not lie. 3i Atlas has an eccentricity greater than 1. Its total energy is positive. It is unbound. It will never return. Picture it this way. Imagine a great cathedral with the sun as a lantern in the center. The planets are dancers, tied to that light by invisible ribbons of gravity, moving in graceful circles and ellipses that never end. Every comet born in this system, every asteroid and ice ball in the distant Oort cloud knows these steps. They may wander far, but the ribbons always pull them back. Into this patient dance floor walks a traveller who was never taught the choreography. It arrives already moving, already carrying momentum from some other place. It bows to the lantern as etiquette demands, arcs politely through the room, and then walks out the far door without looking back. It does not join the dance. It does not learn the steps. It is courteous to our sun, but never ours to keep. The mathematics of this visitor's path were first sketched in early July 2025, when automated surveys flagged a moving point of light beyond 4.5 astronomical units from the Sun. An astronomical unit is simply the distance from Earth to the Sun, about 150 million kilometers, a convenient ruler for measuring the solar system. At 4.5 astronomical units, 3i Atlas was already farther out than the asteroid belt, coasting through the region where Jupiter's gravity dominates. It was moving inward, approaching the Sun on a course that would bring it to its closest point, its perihelion, in late October. That closest approach happens at roughly 1.2 astronomical units from the Sun, a touch inside the average distance of Mars. Not close by human standards, not even particularly close by planetary standards, but close enough that sunlight warms the surface, close enough that if there are ices near the skin of this visitor, they might begin to stir and release gas. Close enough to matter for observations. And then there is the angle. The plane of 3i Atlas is tilted by approximately 175 degrees relative to the plane in which the planets move. To understand what this means, picture the solar system as a flat disk with the Sun in the center and the planets circling in roughly the same plane. Most objects born here share that geometry. They move in the same general direction, following the angular momentum inherited from the original cloud of gas and dust that formed the Sun and planets. A tilt of 175 degrees means 3i Atlas is moving almost directly opposite to this flow. It is retrograde, cutting across the orderly traffic like a vehicle traveling the wrong way on a highway. This is not the behavior of something born here. This is the signature of an object that arrived from a random direction in the galaxy, obeying no local rules, carrying no memory of our system's formation. The angle alone is a clue written in plain sight. This traveler is not from here. Speed tells the second part of the story. At perihelion, estimates place the pace of 3I Atlas at roughly 68 kilometers per second. That is 245,000 kilometers per hour. A number so large, it loses meaning unless you anchor it to something familiar. Light travels at 300,000 kilometers per second. This visitor moves at about 1/4000th the speed of light, which sounds slow until you realize that Earth itself circles the Sun at only 30 kilometers per second. 3I Atlas is moving more than twice as fast as our entire planet. These are speeds earned honestly by falling into the Sun's gravity well on an unbound path. There is nothing mysterious about them. They are simply the natural outcome of carrying excess energy, of being free rather than captured. Conservative calculations place the closest approach to Earth at no nearer than about 1.6 astronomical units, with a mid-December separation of around 1.8 astronomical units. That translates to roughly 270 million kilometers. To put that in perspective, the Sun is about 150 million kilometers from Earth. This visitor will pass us at a distance nearly twice as far as the Sun. It is not a close encounter. It is not a near miss. It is a wide, comfortable margin that leaves no room for concern, no possibility of gravitational disturbance, no chance of collision. The numbers are clear, and they have been checked and rechecked by independent observers using different instruments and methods. The orbit solution is tight. The uncertainty is small. The safe distance is not a guess, it is a measured fact. Why does this geometry matter so much? Because it separates reality from speculation. In the absence of precise measurements, anything becomes possible in the imagination. A faint light in the sky can be a harbinger, a threat, a mystery wrapped in conspiracy. But when you pin down the path with mathematics, when you fit hundreds of observations to the equations of motion, and the solution holds across independent teams and instruments, the story becomes clear. This is a small body, likely a few hundred meters to perhaps a couple of kilometers across, composed of ice and rock and dust, moving on a single pass through the inner solar system before returning to the dark between stars. It poses no danger. It will not stop. It will not hover. It will not change course. It will arrive, bend around the Sun, and depart, exactly as the mathematics predict. And yet, even in this certainty, there is room for wonder. The path may be deterministic, but the visitor itself remains largely unknown. What is it made of? How old is it? Where did it form? And what star did it once orbit? These questions do not have easy answers. They require patient observation, careful measurement, and a willingness to accept limits. Some things we will learn, some things we will only glimpse, and some things will remain hidden, locked in the silence of distance and faintness. The discovery apparatus that found 3I Atlas is worth understanding because it reveals how we have become capable of noticing these faint, fast travelers in the first place. The credit for this detection goes to a network called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System. It is a set of wide-field robotic telescopes designed to scan the sky night after night, looking for anything that moves. The original purpose was sober and practical. Find asteroids that might pose a threat to Earth, find them early, and give humanity time to respond. But the same vigilance that guards against potential impacts also makes Atlas extraordinarily good at catching faint objects that are simply passing through. There is a certain poetry in this. An instrument built to protect our home becomes the tool that discovers messengers from other homes. It is as if we set up a neighborhood watch and ended up noticing travelers from distant countries we never knew existed. The design of Atlas is elegant in its simplicity. Instead of staring deeply at one tiny patch of sky, it sweeps large areas quickly, captures an image, moves on, and then returns to the same area a little later to take another image. Stars, being fixed on the celestial sphere over short timescales, remain in the same positions from one image to the next. But anything moving, an asteroid, a comet, or an interstellar visitor, shifts slightly between frames. Software compares the images, subtracts one from the other, and flags the points of light that have moved. These moving points become candidates for follow-up, and humans review the most promising ones to determine what they are. This patient choreography of look, wait, look again is what makes modern surveys so powerful. The cadence, the rhythm of repeated observations is tuned to catch objects moving at the speeds typical of near-Earth asteroids and distant comets. Too slow, and the object looks stationary, indistinguishable from a star. Too fast, and it becomes a streak or vanishes from the field of view before the second image is taken. But within the sweet spot of a few arcseconds of motion per hour, the detection algorithms are ruthlessly efficient. When several detections line up within a short time window, the software knits them into what is called a tracklet, a tiny arc with a speed and direction on the plane of the sky. A tracklet alone is a whisper. To turn it into a sentence, surveys try to link tracklets from different nights, extending the arc and allowing a preliminary orbit to be calculated. This is where the global coordination becomes essential. There is a clearinghouse for these efforts called the Minor Planet Center, operated by the International Astronomical Union. Observers from around the world send in their measurements, precise positions on the sky, timestamps accurate to the second, and brightness estimates. The Minor Planet Center posts promising candidates on a public confirmation page, a quiet alarm bell that invites other telescopes to look now, not later, because motion carries a faint target away from its predicted position quickly. The window for follow-up can be narrow, especially for fast-moving interstellar objects, and speed matters. Follow-up observations come from telescopes of all sizes. Small backyard observatories with fast cameras can contribute fresh tracklets, extending the arc. Medium and large professional facilities can chase the object with specialized techniques, moving the telescope at the object's rate so that it stays sharp while background stars smear into short lines. For very faint sources, observers stack many short exposures, shifting each image before combining them so that the moving target lands in the same place in every frame. This shift and stack method is a small miracle of patience, pulling a signal from noise, turning a maybe into a yes. While new measurements accumulate, mathematicians fit the data. Each fresh position trims the error bars. Each additional night tightens the orbit. If the path looks like a closed ellipse, the object belongs to our solar system. If it sits near the edge of escape, more data are needed to be sure. If it insists on a wide open curve, the eccentricity climbs above 1 and stays there, and that is the hallmark of an interstellar visitor. The conclusion is not declared on a single, noisy night. It emerges as independent observers using different instruments and different skies arrive at the same answer. When the linked observations keep returning the same unbound solution, When multiple teams measure similar motions and brightnesses, the case becomes solid. The object earns a provisional designation, and if the orbit truly requires interstellar energy, it receives the I label. For 3I Atlas, that progression from first detection to confirmed interstellar status followed the now familiar pattern, but with improvements learned from the first two visitors. There is also a treasure hunt in the past. Once an orbit is sketched, astronomers scour archival images to find pre-discoveries, older exposures, where the object was present but unrecognized. Each earlier detection lengthens the timeline and makes the orbit solution sturdier. Because modern images are calibrated against exquisite star catalogues, those old positions can be remarkably precise. A single pre-discovery from months earlier can shrink the corridor of uncertainty dramatically, like adding a distant fence post that suddenly makes a winding path clear. All the while, the same frames used for pinning down position also carry photometry, simple measures of brightness through standard filters. If the point looks fuzzier than nearby stars, that can hint at a faint coma, a haze of gas and dust. If brightness rises faster than geometry alone predicts, outgassing may be adding reflective area. None of these signs are taken in isolation. Teams compare notes, check for instrumental quirks, repeat measurements on nights with steadier air. The process is careful, methodical, and communal. What makes this apparatus so effective is that it invites serendipity. Surveys like Atlas, Pan-STARRS, Catalina, and the Zwicky Transient Facility do not wait for special events. They create the conditions to notice them. Wide fields catch more sky in fewer exposures. Rapid repeats build those crucial tracklets. Automated pipelines never tire of comparing frames, and global coordination turns a local hint into a worldwide campaign, with observatories trading clouds and daylight across time zones to keep the target in view. When 3I Atlas was flagged in early July, the global network responded. Positions were measured, brightnesses recorded, colors estimated through filters. The arc grew longer, the orbit solution tightened, and the eccentricity settled comfortably above 1. By the time the announcement was made, there was no doubt. This was the third confirmed interstellar object, and the machinery of discovery had worked exactly as intended. But discovery is only the beginning. Finding the visitor is one thing. Understanding it is another. What dimness hides is where the real story begins. Atlas is faint, not invisible, but far from the bright comets that make headlines and draw crowds. It lives in the realm of magnitudes in the positive teens, a brightness that requires telescopes, patience, and careful technique to observe. To the unaided eye, it would be utterly invisible, even under the darkest skies. To small backyard telescopes, it is a challenge, a faint smudge that appears only in stacked images taken over hours. To professional observatories, it is a measurable target, but still one that demands respect for the limits of detection. The magnitude scale is astronomy's way of keeping score with brightness. It is an old system dating back to ancient Greece, where the brightest stars were called first magnitude, and the faintest, visible to the naked eye, were sixth magnitude. The scale has since been refined and extended, but it retains its counterintuitive structure. Smaller numbers mean brighter objects. A difference of 5 magnitudes corresponds to a factor of 100 in brightness. The full moon sits around magnitude -13. Venus at its brightest is about -4. The faintest stars visible to the naked eye under perfect conditions are around magnitude 6. The faintest objects detectable by the largest ground-based telescopes push beyond magnitude 28. 3I/Atlas, depending on its distance and activity level, hovers somewhere in the range of magnitude 18 to 20. That places it firmly in telescopic territory, well beyond the reach of casual observation. To put this in perspective, an object at magnitude 18 is roughly 4,000 times fainter than the faintest stars you can see with your eyes. It is a whisper of light, a handful of photons arriving each second, competing against a background of airglow, moonlight, city glow, and the inherent noise of the detector. Detecting such faint objects is less about heroic single exposures and more about patience and technique. Long exposures help, letting photons accumulate over minutes or even tens of minutes. But long exposures also accumulate noise. The atmosphere has its own faint glow, a product of chemical reactions high in the upper layers. The moon, even when not full, throws a wash of scattered light across the sky. Cities contribute their share of light pollution. And the detector itself, a sensitive electronic chip cooled to reduce thermal noise, still registers a small hiss of random electrons when it is read out. The art of measuring faint light is the art of separating signal from noise. One approach is to take many shorter exposures instead of one long one. Short frames avoid trailing if the telescope tracking is imperfect. They reduce the chance that a passing satellite or cosmic ray will ruin the only shot. And when you combine many images after carefully calibrating them, the true signal grows steadily, while the random noise grows more slowly, roughly with the square root of the number of images. The result is a cleaner detection, a firmer measurement, a more trustworthy sentence. Calibration is the housework that makes everything work. Before the night's observations begin, astronomers take bias frames with the shutter closed, measuring the detector's electronic offset. They take dark frames, long exposures with the shutter closed, to record the thermal noise. They point at an evenly illuminated surface, often the twilight sky, and take flat field images that map out the pixel-to-pixel sensitivity and the shadows cast by dust on the optics. These calibration frames are subtracted and divided from the science images, removing the predictable sources of error and leaving only the light from the sky. Then comes background subtraction. The sky is never truly black. Even far from city lights, even on moonless nights, the background glows faintly. To measure the brightness of a faint object, you must first measure the brightness of the sky immediately surrounding it and subtract that value. This is done carefully, choosing an annulus or ring around the object where no other stars or galaxies contaminate the measurement. The result is a brightness estimate for the object alone, freed from the glow of the background. For a moving target like 3I/Atlas, there is an additional complication. If the frames are taken with the telescope tracking the stars, the visitor will drift across the field, leaving a short trail. For very faint objects, that trail dilutes the signal. The solution is shift and stack. Before combining the images, each frame is shifted so that the target lands in the same position. Then they are added together. The stars turn into small streaks, but the visitor pops into focus, its light concentrated into a single bright point. This technique can pull whispers out of noise, revealing objects that are invisible in any single frame. Once the object is detected, measuring its brightness becomes a matter of aperture photometry or point spread function fitting. Aperture photometry places a small circular opening around the target, sums the light inside, and subtracts the contribution from the local sky. It is simple and robust, but the size of the aperture matters. Too small, and you lose the faint wings of the blurred image. Too large, and you swallow extra noise. Point spread function fitting, on the other hand, models the exact shape of how a star's light is blurred by the atmosphere and optics, and scales that model to the target. In crowded fields or poor seeing, Fitting can extract more accurate numbers. For an object with a faint coma, a hybrid approach helps. Model a point-like core plus a shallow extended halo and measure both. Noise has many personalities. Photon shot noise is unavoidable, a consequence of the fact that light arrives in discrete packets, and the number of photons detected in any given exposure fluctuates randomly. Even a perfectly steady light source produces jittery measurements. Then there is read noise from the detector electronics, pattern noise from imperfect calibration, and variations in atmospheric transparency. On windy nights, the stellar images dance and swell. On hazy nights, thin clouds steal photons without making the sky look obviously cloudy. All of this means that every brightness measurement comes with an error bar, a range of uncertainty that reflects how much the measurement might differ from the true value. Error bars are not apologies. They are information. They tell you how much weight to give a particular data point, how confidently you can compare measurements from different nights or different telescopes. When several independent observations agree within their error bars, confidence grows. When they do not, something interesting is happening, or something went wrong, and careful investigation is needed to figure out which. Astronomers often set a threshold for claiming a detection. A common standard is 5 sigma, meaning the signal must stand 5 standard deviations above the noise expected from the background. This reduces false alarms, which are more likely than intuition suggests when you are searching thousands of pixels across hundreds of frames. But it also means that very faint objects, those hovering just at the edge of detectability, may be seen on some nights and missed on others. In those cases, upper limits are reported. Fainter than this magnitude with such and such confidence. Upper limits are not failures. They are constraints, fences that tighten the space where the truth can live. For a faint interstellar visitor like 3I Atlas, every photon matters. The object is distant, small, and not particularly reflective. If it has a coma, a haze of dust lifted by sublimating ice, that coma is subtle, not the dramatic tail of a bright comet. If it is rotating, and its shape is irregular, the brightness will flicker as different faces catch the sunlight. If non-gravitational forces, tiny jets of escaping gas, are nudging its path, those effects will be small, detectable only through meticulous astrometry over many nights. This is where patience transforms into knowledge. Each observation, each carefully calibrated image, each shift and stack combination adds another sentence to the story. The brightness rises and falls with distance, revealing the interplay of geometry and activity. The colors measured through different filters hint at surface composition, the balance of dust and ice, the weathering from cosmic rays and micrometeorites. The positions measured night after night trace the path with increasing precision, and when fitted to models, reveal whether tiny accelerations are present. Whispers of outgassing, invisible to cameras but loud in the mathematics of motion. What dimness hides is not emptiness. It is detail, waiting for the right tools and the right patience. A faint smudge on a detector, dismissed by a casual glance, becomes, under careful scrutiny, a rotating body with hints of surface texture, a traveller from another star, carrying clues about its birthplace and its long journey through the cold. The art of seeing little, of turning a flicker at the threshold into a trustworthy measurement, is one of astronomy's quiet superpowers. It does not make for dramatic images or viral headlines, but it makes for knowledge, steady and reliable, the kind that accumulates slowly and lasts. Activity is a word astronomers use to describe what happens when sunlight warms the surface of a small icy body enough to release gas. That gas, invisible in ordinary photographs, lifts dust into space, and that dust reflects sunlight, turning what would be a single star-like point into a soft blur surrounded by a faint haze. This haze is called a coma. If enough gas and dust are released, and if the geometry is right, a tail can form, always pointing roughly away from the sun, pushed by light pressure and the solar wind. The presence or absence of a coma, the brightness and structure of that haze, the subtle changes in color and profile, all of these carry information about what the object is made of, where it formed, and how its surface has weathered during the long cold between stars. For 3I Atlas, the question of activity is delicate. This is not a bright, photogenic comet with an obvious tail splashed across the sky. It is a faint object, and any coma it produces is likely to be subtle, detectable only through careful comparison with nearby stars and patient stacking of many images. Some observations show a profile that is just slightly wider than the sharp point spread function of background stars, consistent with a thin halo of dust. Other nights, the profile looks essentially stellar, indistinguishable from a rock with no atmosphere at all. This disagreement is not a clash of interpretations. It is a consequence of seeing conditions, instrument resolution, and the changing geometry as the object moves closer to and then away from the sun. The coma, if present, tells a story about composition. Water ice is the most familiar volatile, but it requires significant sunlight to sublimate. At distances beyond about 3 astronomical units from the sun, water ice tends to remain frozen and inactive. Closer in, especially inside 2 astronomical units, water can begin to turn from solid to gas, releasing molecules that lift dust grains into space. But water is not the only ice that matters. Carbon dioxide and carbon monoxide are more volatile. They can sublimate at much greater distances, stirring a coma even when water remains locked in the surface. An object that shows activity far from the sun, beyond 5 astronomical units, is likely rich in these more easily vaporized ices. An object that remains quiet until it approaches perihelion may have a surface crusted with less volatile material, or may be dominated by water ice that only wakes when the sunlight grows strong. The challenge with 3I/Atlas is that it is faint enough that detailed spectroscopy, the gold standard for identifying gases, is difficult. Spectroscopy spreads the light out into a rainbow and looks for the characteristic fingerprints of molecules. In visible light, classic cometary signatures include emission bands from cyanogen, a fragment of more complex molecules, and from diatomic carbon. In the ultraviolet, hydroxyl traces the breakup of water, acting as a proxy for water production. In the infrared, carbon dioxide and carbon monoxide leave their own features. When these bands are present, activity is confirmed. When they are absent, down to a firm detection limit, it suggests either that the gases are too faint to see, or that the surface is not producing them in measurable quantities. For a distant, faint visitor, spectroscopy becomes a game of balancing exposure time against signal-to-noise ratio. Long exposures gather more light, but the object is moving, and keeping it centered in a narrow slit or fiber takes careful tracking. Background light from the sky must be subtracted, and that background itself can carry faint emission lines that confuse the analysis. The result is that even with large professional telescopes, the spectra of 3I Atlas are likely to be marginal, offering hints rather than certainties, upper limits rather than detections. This is not a failure of technique. It is simply the honest limitation of measuring something so faint and so far away. Color indices provide a gentler way to probe composition. By measuring the brightness through different filters, blue, green, red, and sometimes near-infrared, astronomers can calculate simple color ratios. A surface that reflects red light better than blue appears reddish. A surface that reflects both equally appears neutral grey. These small differences, gathered with care, are the first clues to surface texture and chemistry. Reddish colours are common among cometary dust and many distant small bodies. Long exposure to cosmic rays, high-energy particles that constantly bombard objects in space, tends to darken surfaces and build complex carbon-rich molecules, often called tholins. These materials absorb blue light more strongly than red, giving the surface a ruddy hue. Fine grains also scatter blue light differently than red, contributing to the overall color. Neutral colors, on the other hand, can point to larger, darker grains, or to surfaces that have been heated enough to bake away the most delicate organic coatings. A faintly bluish cast sometimes hints at very small, fresh grains, lifted recently by activity, or at unusual mineral compositions. For 3-eye atlas, early color measurements suggest a slightly reddish tone, placing it comfortably within the broad family of dusty small bodies whose surfaces have weathered in the cold for a very long time. This is not surprising. If the object formed in the outer regions of another planetary system, beyond that system's snowline where ices are stable, and then drifted through interstellar space for millions or billions of years, cosmic rays would have had ample time to darken and redden the surface. The slight redness is a quiet signature of age and exposure, not a dramatic revelation, but a consistency check that the story fits together. The profile of the light, how it spreads out around the central point, offers another clue. A star, even when blurred by the atmosphere and the telescope optics, has a characteristic shape called the point spread function. It is brightest at the center and fades smoothly outward, dropping off in a predictable way. A comet with a coma has a profile that is wider and shallower. The central nucleus is still there, a bright peak, but surrounding it is a diffuse glow from dust suspended in space. By comparing the profile of the target to the profiles of nearby stars in the same image, astronomers can tell whether the extra width is real or just an artifact of slightly different seeing. If the profile is genuinely wider, the next step is to model it. A simple approach treats the coma as a smooth halo with brightness that declines as some power of distance from the center. A more sophisticated approach separates the point-like nucleus from the extended coma, fitting both components simultaneously. This separation matters because a bright coma can make a tiny nucleus look deceptively large. The goal is to back out the brightness of the solid core and place limits on its size, which in turn requires assumptions about how reflective the surface is. A dark surface implies a larger object. A brighter surface implies a smaller one. Without independent constraints on reflectivity, size estimates come as a range rather than a single number, and that range can be discouragingly wide. One useful shorthand for dustiness is a parameter called AFRA, pronounced like afro. It condenses albedo, dust production, and the size of the measuring aperture into a single number with units of length. Larger values generally mean more dust in the coma. It is not a perfect measure, but it lets observers compare results from different nights and different telescopes on a common scale. If AFRA rises as the object approaches the sun, that suggests increasing activity. If it remains low and steady, that suggests a quiet surface with minimal outgassing. Sometimes, activity hides. A body can be shedding gas that is too tenuous to glow strongly in emission bands. or the dust grains can be large and dark, making the coma low in contrast against the background sky. In those cases, variability becomes the clue. If the brightness undulates with a rhythm that does not match the expectations from changing distance alone, rotation and patchy jets may be at work. A nucleus that is not a perfect sphere, and few small bodies are, will present different cross-sections to sunlight as it spins. Bright patches and dark patches rotate in and out of view, causing the reflected light to flicker. By plotting these small ups and downs in brightness over time, astronomers can tease out the rotation period and get hints about the shape. An elongated object, tumbling end over end, produces large amplitude variations. A nearly spherical object, with subtle surface markings, produces smaller, gentler variations. For 3i Atlas, early light curves suggest small, regular flickers consistent with rotation. The size of those flickers implies that the body is not perfectly round. Whether it is elongated like a potato, flattened like a disc, or simply irregular with hills and valleys, remains uncertain. Dense monitoring over many nights, stitched together across different longitudes and time zones, could break the ambiguity and reveal the true shape. But such campaigns require coordination and luck with weather, and the window for observation is limited. The visitor will not wait. It moves according to the mathematics of its orbit, and once it passes perihelion and begins its long climb back toward interstellar space, it will fade quickly, becoming too faint for detailed study. The connection between activity and composition is not straightforward. A quiet surface does not necessarily mean a lack of ice. It could mean that the ice is buried beneath a layer of dust, an insulating mantle that prevents sunlight from reaching the volatile material below. As gas escapes from deeper layers, it lifts dust, and that dust can settle back down, gradually building up a protective crust. Over time, this crust can seal the surface, choking off further activity, even as ices remain abundant just beneath. Conversely, a lively coma does not guarantee a pristine icy surface. It could be that the dust is unusually fine and reflective, making even modest gas production look dramatic in images. Or it could be that localized jets, small active patches on the surface, are producing gas while the rest of the body remains dormant. This is why multiple lines of evidence matter. A faint cyanogen emission band, paired with a slight non-gravitational nudge in the motion, would strongly suggest that vents are present, even if the coma stays shy in ordinary images. A reddish color, a gentle forward scattering surge when the sun object Earth angle is small, and a thermal hint of silicate dust would paint a coherent picture of aged, dusty material. A nearly neutral color, a flat brightness curve with phase angle, and no detectable gas bands would point toward coarser grains and a modest or sealed surface. Each line of evidence stays light on its feet, acknowledging uncertainty, but together they walk in step, building a portrait that is more reliable than any single measurement could provide. In the end, what the coma reveals, or what its absence suggests, is a fragment of the visitor's biography. The balance of ices and dust, the thickness of any crust, the presence or absence of active vents, all of these speak to where the object formed in its birth system, how close it passed to that system's star before ejection, and how its surface aged during the long drift through the galaxy. It is a quiet form of archaeology, reading history from light. Non-gravitational forces sound exotic, but they are simply the tiny pushes that occur when an object is not perfectly inert. The dominant force shaping the path of 3i Atlas is gravity, the pull of the sun bending the trajectory into its characteristic hyperbolic arc. But if the surface is releasing gas, those escaping molecules carry momentum. When they leave the surface, they push back, like a miniature rocket exhaust. The push is gentle, many millions of times weaker than the pull of gravity, but over weeks and months it accumulates. Careful measurements of position, precise astrometry, can detect these tiny deviations from a purely gravitational path. The way astronomers describe these nudges is through a simple coordinate system tied to the orbit itself. One axis points directly away from the Sun, the radial direction. One axis lies along the direction of motion, the transverse direction. And one axis is perpendicular to the orbital plane, the normal direction. A push in the radial direction, away from the Sun, occurs when gas escapes preferentially from the sunlit side. This is the most common scenario for active comets. Sunlight warms a patch of surface, ice sublimates, and gas vents outward, pushing the nucleus slightly away from the Sun. This radial push does not change the orbital period much, but it does shift the timing of when the object reaches certain points in its orbit. A push in the transverse direction, along or against the direction of motion, acts a bit like tapping the accelerator or brake. If gas escapes more strongly from the afternoon side of the nucleus, as it rotates, the push can add to the velocity. If it escapes more strongly from the morning side, it can subtract from the velocity. These transverse forces can stretch or shrink the orbital solution slightly, altering the semi-major axis and the period. A push in the normal direction, out of the orbital plane, tips the path, tilting the orbit by small angles that add up over time. For an unbound hyperbolic orbit, these effects do not change the fundamental geometry. The eccentricity remains above 1, but they do fine-tune where the object appears on the sky and when. Detecting non-gravitational forces requires a long, clean time series of astrometric measurements. Each observation records the position of the object against the background stars, accurate to a fraction of an arcsecond. The precision needed is extraordinary. A shift of a few tenths of an arcsecond over weeks can be the signature of a tiny acceleration. To achieve this, observers use well-calibrated star catalogues, correct for atmospheric refraction, and carefully model the point spread function to determine the exact center of the object's light. If the object has a coma, a lopsided dust distribution can bias the measured position away from the true center of the nucleus. This is called the photocenter offset, and it can masquerade as a non-gravitational effect if not handled carefully. To mitigate this, teams model the coma's brightness profile, compare it to nearby stars, and use small apertures or specialized fits to keep the centroid honest. They also weight observations differently depending on the quality of the seeing, the stability of the tracking, and the signal-to-noise ratio. Outliers, measurements that disagree strongly with the overall trend, are either given less weight or excluded entirely. The goal is to let the data speak without being drowned out by noise. When several independent teams, using different telescopes, cameras, and analysis pipelines, recover the same small acceleration with compatible values, confidence grows. The signal is real. Something beyond pure gravity is nudging the path. For 3I Atlas, the question is whether such accelerations will be detected, and if so, how strong they are, and in which directions they point. A strong radial component would suggest dayside vents. A strong transverse component would hint at asymmetries in how the surface heats and cools, perhaps tied to rotation. A lack of any detected push would set clean upper bounds. Either the surface is truly inert, or the outgassing is so weak that current instruments cannot measure its effect on the orbit. Outgassing does more than push. It can twist. If the vents are not located at the rotational poles, but rather on the sides of the nucleus, they exert torques that speed up or slow down the spin. Over time, the rotation period can drift by measurable amounts. In extreme cases, rapid spin-up can pull a loosely bound object apart, fragmenting it into smaller pieces. In milder cases, the changing spin simply alters the light curve, shifting the times when bright and dark patches face the sun. This feedback between activity and rotation is why some comets show asymmetric behavior before and after their closest approach to the sun. The same regions of the surface are not being heated in the same way on the outbound leg because the spin has changed. Not every nudge comes from gas. Sunlight itself pushes on dust and on very low mass, high area surfaces through radiation pressure. For large compact nuclei, this effect is negligible, but for fine grains suspended in a coma and for unusually light, flaky fragments, the effect is real. Thermal forces can matter even for bare rocks. As a small dark object warms on its afternoon side and re-radiates heat, the recoil from that emitted infrared light can slowly shift its orbit. This process, known as the Yarkovsky effect, is well studied for near-Earth asteroids. For an active, dusty traveler like 3I/Atlas, outgassing is expected to dominate while the ices are lively, with radiation pressure mostly sculpting the dust tail rather than steering the nucleus. The modeling of non-gravitational forces is an art that balances physical plausibility with mathematical simplicity. The classic approach keeps gravity as the foundation and adds three small terms, scaled by smooth functions that represent how sublimation tends to rise and fall with solar distance. These scaling functions can be tuned for different ices. A water-like curve that brightens inside a few astronomical units, or a carbon monoxide curve that activates farther out. The software fits the model to the astrometric data, solving for the tiny coefficients that best reduce the residuals, the differences between predicted and observed positions. Because the signals are small, uncertainty deserves an honest seat at the table. Star catalogues carry their own errors. Atmospheric seeing changes from minute to minute. A slightly smeared image can move the centroid by a fraction of a pixel. To handle this kindly, orbit solvers propagate full covariance matrices, mathematical structures that track how uncertainties in one measurement relate to uncertainties in others. They test the robustness of the solution by removing subsets of the data and refitting, checking whether the result holds. When it does, trust accumulates. Another useful habit is to allow the model to evolve with time. Some approaches permit the peak activity to lag behind the moment of closest approach, reflecting thermal inertia in the surface layers. The surface does not warm instantly when the sun's intensity increases. There is a delay as heat diffuses inward. Similarly, the surface does not cool instantly as the object moves away. This lag can shift the timing and direction of maximum gas production, creating asymmetries between the inbound and outbound legs of the trajectory. What does a detected non-gravitational acceleration imply? First, it is evidence for escaping gas even when images look nearly stellar. The orbit remembers what the camera cannot see. Second, the direction and strength of the fitted terms hint at where vents might be located and how the object is spinning. A strong push directly away from the sun suggests vents on the subsolar hemisphere, the side facing the star. A push along the direction of motion reveals that the warmest regions are offset from local noon, perhaps because the surface takes time to heat, or because the spin axis is tilted in a particular way. Third, the total thrust budget, integrated over the passage, tells something about how much material is leaving the surface. Small in absolute terms, but meaningful over the timescale of the encounter. There are also helpful negatives. If positions remain perfectly gravitational within the measurement noise, that does not prove the surface is inactive. It simply sets an upper limit on any jetting. If color and spectra show no obvious gas features, activity could still be dominated by large, dark grains that are hard to detect. And if different teams recover slightly different small accelerations, the cause may be mundane: differing apertures, different seeing conditions, or varying coma structure on different nights. The key is to let multiple lines of evidence agree before making strong claims. In the end, non-gravitational modeling is less a dramatic reveal and more the art of listening for a whisper while an orchestra plays. Gravity takes the lead, writing the main melody with bold, sweeping curves. Outgassing, radiation pressure, and thermal effects add faint harmonics. Once heard and measured, those harmonies make the whole piece clearer. For an interstellar visitor like 3I Atlas, these gentle pushes turn brightness and chemistry into motion, letting a quiet smudge of light disclose its vents, its spin, and a fragment of the landscape from which it first learned to breathe. The interstellar family, small as it is, offers a chance to compare. Line up the 3 confirmed visitors and notice first the shared traits. Each one carries more energy than the sun can hold. Each follows an open hyperbolic path with eccentricity greater than 1. Each writes a single graceful line through the solar system before vanishing. All 3 were found by vigilant watchers, some human, some robotic, who blink images of the night and notice motion. And all 3 are small, faint, and fast enough that time with them is precious, a narrow window between detection and departure. In the quiet light of those facts, 1I ʻOumuamua, 2I Borisov, and 3I Atlas look like siblings, distant, brief, and instructive. But now let the differences speak, because that is where the richness lies. ʻOumuamua was the puzzler. Discovered in October 2017, it was already on its way out, having passed perihelion weeks earlier. The observing window was short, a matter of weeks before it faded beyond the reach of even large telescopes. In that brief time, it revealed unusual behavior. Its brightness swung dramatically as it rotated, with a range suggesting a highly elongated or flattened shape, something like a cigar or a pancake tumbling through space. No clear coma or tail appeared in ordinary images, leading some to wonder whether it was more like a rocky asteroid than an icy comet. Yet its motion showed a tiny, non-gravitational acceleration, a gentle push that could not be easily explained by known forces. The likely causes discussed by scientists included subtle outgassing of ices that do not produce visible dust, unusual surface properties that allow radiation pressure to act more effectively, or perhaps hydrogen ice that sublimates without leaving an optical signature. With only a short arc of data and no chance for follow-up, many questions remained open. ʻOumuamua is the riddle that politely walked out mid-sentence, leaving more mysteries than it solved. Borisov, discovered in August 2019, was the opposite personality. It arrived well before perihelion, giving the global community months to prepare and observe. It behaved in many ways like the long-period comets born in our own solar system. It had a visible coma that grew as it approached the sun. It developed a clear tail, swept by sunlight and solar wind. Spectra revealed emission bands consistent with ordinary cometary materials: water, carbon monoxide, and dust rich in silicates. Some measurements suggested a generous supply of carbon monoxide, hinting at formation in a very cold environment. The nucleus was roughly on the kilometer scale, perhaps a bit smaller. The tail was photogenic, visible in images from small backyard telescopes to the largest professional instruments. Observers followed it for months, building a rich data set of colors, spectra, light curves, and non-gravitational accelerations. If ʻOumuamua whispered strange, Borisov said familiar. It was a comet from somewhere else, yes, but it looked and acted like the comets we know. 3I Atlas, on present evidence, sits between those two extremes. Its trajectory marks it as interstellar beyond doubt. The eccentricity is secure. The path is open. Its brightness and color behavior suggest activity that may be present, but modest, depending on geometry, distance, and the state of the surface. The orbit is steeply tilted, nearly opposite the traffic of the planetary system, a geometric signature that screams outsider. Its closest approach to the Sun keeps it well away from Earth, and while it may not become a naked-eye spectacle, the light it reflects can still be weighed and read. Less theatrical than Borisov, less enigmatic than ʻOumuamua, and valuable precisely because it expands the sample. Each new visitor fills in a different part of the picture, showing that the population is diverse, that interstellar space exports both inert-seeming fragments and lively ice balls, with quiet intermediates in between. Comparison sharpens intuition. Start with appearance. ʻOumuamua looked star-like in images, no obvious fuzz, no tail, just a point that brightened and dimmed with large amplitude as it tumbled. Borisov looked textbook cometry, a soft coma surrounding a point-like core, and a tail swept back by light and wind. 3I Atlas likely shows a profile that widens beyond a stellar point when warmed, evidence of dust lifting into a coma. Yet the display remains faint enough that careful stacking and profile checks do the heavy lifting. 3 looks, 3 lessons. Interstellar space exports a variety of products, not a single type. Then listen to the motion. All 3 are unbound, but the way they moved across the sky felt different. ʻOumuamua's late discovery meant it was already racing away, leaving only a short arc of precise positions from which to infer a lot. The rapid fade limited spectroscopy and detailed follow-up. Borisov's earlier detection provided a long, comfortable arc, months of tracking that tightly constrained the orbit and allowed detailed studies of activity as it evolved with solar distance. 3I Atlas benefits from improvements in survey vigilance, flagged farther out than was common a decade ago, giving the community time to plan observations near perihelion and beyond. As detection capabilities stretch earlier, reaching farther into the outer solar system, the science stretches with it. Rotation rates, color changes, and non-gravitational nudges can be tracked more calmly, without the frantic urgency of a rapidly closing window. Composition and activity draw another contrast. ʻOumuamua's lack of obvious gas signatures forced creative hypotheses. Could it be outgassing molecules that do not emit light in the visible or near-infrared? Could its surface have unusual properties, perhaps a shiny, reflective crust that amplifies radiation pressure? Could it be composed of something we have not considered, like solid hydrogen or nitrogen ice? Borisov's spectra showed the familiar fingerprints of cometary gases and dust, with some ratios suggesting formation in a cold birthplace, but nothing fundamentally alien. 3I Atlas, being fainter, invites a more forensic approach. Colors through broad filters, careful light curves, and orbit fits that check for tiny accelerations. Even limits, no clear gas band detected, no strong non-gravitational term found. Feed the picture by narrowing what the surface can be. The absence of evidence, when carefully measured, becomes evidence of absence, or at least evidence of subtlety. What do the differences teach? First, they argue for diversity. Planetary systems seem to eject a wide range of fragments. Some are dusty and volatile, rich in ices that wake easily. Some are crusted or depleted, their surfaces sealed by mantles of dust, or baked by repeated passes near their parent star before ejection. Some might be compact shards with little exposed ice, tumbling rocks rather than dirty snowballs. The population is not uniform. Second, the differences show how selection affects first impressions. A bright, active comet is easier to notice and characterize. Telescopes can gather spectra, track light curves, measure colors with confidence. A small, inert-looking shard can slip by unless surveys are both wide and quick, covering large areas of sky with enough sensitivity to catch faint movers. The growth of automated sky monitoring networks means the ledger of interstellar visitors is likely to fill with many types, not just the photogenic ones. Third, the trio reinforces a quiet truth about evidence and labels. The interstellar designation rests on geometry and energy, not on having or lacking a tail. ʻOumuamua, Borisov, and 3I Atlas all cross the Sun's neighborhood with eccentricities greater than 1 and positive total energy. Whether they wear a veil of dust or keep a bare face is a separate, equally interesting question, one that speaks to composition, age, and surface processing during untold years in the cold. The orbit tells you where it came from, in the sense of bound versus unbound. The appearance and activity tell you what it is made of and how it has weathered. There is also a human lesson hiding in the timelines. ʻOumuamua arrived early in the era of modern wide-field surveys, and its mystery partly reflects the shortness of the observing window. The community learned, instruments improved, alert systems became faster, and 2I Borisov became a long, shared campaign involving dozens of telescopes and hundreds of observers. 3I Atlas benefits from that accumulated experience. Better pipelines flag candidates sooner. Faster alerts reach the global network within hours. Coordinated follow-up turns a provisional detection into a confirmed interstellar visitor in days rather than weeks. Each traveler leaves not only data, but also better habits for greeting the next one. Lay the three side by side, and the family portrait feels satisfying. One sibling is the quiet enigma, star-like and swift, hinting at exotic surfaces or subtle forces we do not fully understand. One is the classic comet from a foreign nursery, rich in dust and gas, comforting in its familiarity, even as it speaks of another sun. One is the measured guest with a tilted road and modest glow, a reminder that the cosmos rarely repeats itself exactly. Together they say that other planetary systems build, weather, and eject small bodies in many ways, and that our solar system is open to brief visits from all of them. The door is not locked. The sky is not a closed room. Travelers pass through, and if we watch carefully, patiently, with the right tools and the right cadence, we can learn from each one. Origins are where stories become speculation, but educated speculation, grounded in physics rather than fantasy. Where did 3I Atlas come from? Not in the sense of a specific star, that information is almost certainly lost, but in the sense of process, of mechanism, of the forces that shape planetary systems and decide which fragments stay and which are thrown away. Every interstellar visitor is a castaway, an object that was once part of a forming planetary system, and then, through a series of gravitational encounters, gained enough energy to break free. Understanding how that happens, how nature builds ejection into the very architecture of star and planet formation, is to understand something fundamental about how common these travelers might be. Imagine a young star wrapped in a wide, thin disk of gas and dust. This is the birthplace of planets, a nursery where grains collide and stick, where snowflakes of ice collect into pebbles, and pebbles grow into boulders, and boulders into planetesimals, small worlds too numerous to name. Most of these planetesimals never become planets. They are the leftovers, the rubble that records the recipe. In every active nursery, gravity and time sift this rubble. Some pieces are swept up by growing planets. Some are ground down in collisions, pulverized into dust. And some are hurled away, ejected on paths that do not return. The most common ejection mechanism involves giant planets. Jupiter and Saturn in our own solar system are natural slingshots. When a small icy body passes near a massive planet, the encounter can act as a gravity assist, trading momentum between the two. The planet, being vastly more massive, barely notices. The small body, being light, can have its velocity changed dramatically. A single pass might nudge it into a new orbit, still bound, but different. Repeated passes, gravitational pinball played over thousands or millions of years, can pump up the energy until the small body crosses the threshold and leaves the star entirely. The process is efficient, especially in systems where giant planets have migrated, moving inward or outward through the disk. Migration stirs the planetesimal sea, pushing and pulling swarms of fragments across orbital resonances that amplify encounters. A few planetesimals are swallowed by the giants. Many are scattered inward, sometimes into the inner system, where they may collide with terrestrial planets or be consumed by the star, and a great number are ejected outward, given enough energy to escape. The numbers are staggering. Models of our own solar system's early history suggest that during the era when the giant planets settled into their current orbits, possibly undergoing a phase of rapid migration called the Late Heavy Bombardment, trillions upon trillions of small icy bodies were ejected. Most of those objects are now wandering the galaxy, unbound fragments carrying faint memories of the sun's nursery. If our system did this, and the physics suggests it did, then every system with giant planets likely does the same. The galaxy should be quietly full of these castaways. Binary stars raise the stakes. With two stars orbiting each other, the gravitational landscape becomes more complex. There are zones where orbits are simply unstable, regions where a small body cannot maintain a stable path over long timescales. A fragment that strays into one of those zones finds itself in a chaotic three-body dance, tugged by both stars in ways that amplify over time. In a handful of close passages, the object can be accelerated to escape velocity without needing help from giant planets. Observations show that binary systems are common in the galaxy. Perhaps half of all stars have a companion. If binary dynamics provide a quicker, more efficient ejection channel, then the contribution to the interstellar population could be substantial. There is a quieter route as well, through the environment of star birth. Most stars form in clusters, crowded neighborhoods where dozens or hundreds of young stars are packed into a volume just a few light-years across. These clusters live for a few tens of millions of years before the stars drift apart, dispersing into the wider galaxy. During that time, the stars are close enough that they occasionally pass within a few thousand astronomical units of each other. Those flybys, though brief, can tug on the wide outer orbits of material surrounding each star. An outer reservoir, something like the hypothetical Oort cloud around our Sun, a vast sphere of icy fragments tens of thousands of astronomical units out, can be shaken by a passing neighbor. Some bodies are nudged inward, perhaps later becoming long-period comets. Some are pulled outward, stripped away entirely, and sent into interstellar space. The cluster years are turbulent, and many small worlds learn their fates there. Early ultraviolet light from massive neighbors can also play a role. Hot, bright stars in a cluster flood the environment with intense UV radiation. This radiation can strip gas from the outer parts of protoplanetary disks, eroding them and changing which ices survive near the surface. Material that would have formed rich in volatile ices might instead be baked and depleted. When fragments from such disks are later ejected, their surfaces carry the signature of that early processing, crusted and reddened, with volatile ices buried or lost. Composition sets the initial conditions. A fragment forming beyond the local snow line, the distance from the star where water ice is stable, will carry a cold chemistry. Water ice, carbon monoxide, carbon dioxide, and a mix of complex organics frozen onto silicate dust grains. If it forms inside the snow line, the surface will be drier, rockier, dominated by silicates and metals rather than ices. Later processing can blur these boundaries. Repeated close passes to the star before ejection can bake the surface, building a crust of refractory material that seals in whatever ices remain below. Collisions can expose fresh ice or shatter a parent body into irregular shards that tumble and present unfamiliar shapes. By the time such a fragment is ejected, its surface may be armored and darkened, weathered by radiation and impacts, while just beneath, pristine ices remain preserved from the original formation. The launch itself can happen early or late in a system's evolution. Early ejections occur while the disk is still present, while gas drag damps some orbits and amplifies others, shepherding planetesimals toward resonances with growing giants. This is a dynamically hot phase, chaotic and efficient at clearing debris. Late ejections play out over hundreds of millions or even billions of years, as slow gravitational perturbations gradually reshape a system's architecture. A small change near a massive planet, repeated over countless orbits, can eventually become a decisive kick. The solar system's own history likely included a phase when the giant planets shifted their distances, a rearrangement that traded angular momentum and ejected large numbers of icy bodies. There is no reason to think other systems do not experience similar reshufflings. Can the incoming direction of an interstellar traveler reveal its birthplace? Usually not with any precision. By the time a fragment reaches us, its original velocity has been altered by encounters with its home planets, shaped by the gravity of its parent star during ejection, and then gently perturbed over vast timescales by weak tugs from passing stars and the tidal forces of the galaxy itself. The velocity vector at arrival is a story written by many hands, layer upon layer of influence, and unpacking those layers to identify a specific star of origin is nearly impossible. Only in rare cases, when an ejection is very recent, geologically speaking, and the fragment arrives with a velocity close to that of a nearby, well-measured star, might a plausible parent be suggested. For most visitors, the responsible system remains an unnamed neighbor in the galactic crowd. Still, the neighborhood matters in broad strokes. Around cooler, smaller stars, red dwarfs and orange dwarfs, the snow line sits closer to the star. Icy planetesimals can form nearer in, where gravitational stirring from planets is stronger. Around hotter, larger stars, the snow line lies farther out, offering a wide field for icy growth, but also making those bodies more loosely held by the star's weaker relative gravity at that distance. Dense clusters with frequent stellar flybys should export more interstellar debris per star than sparse regions where stars form in isolation. Systems with multiple giant planets are efficient ejectors, capable of clearing vast amounts of rubble. Systems without giants may trap more debris long-term, leaving it in distant reservoirs rather than flinging it away. Over the lifetime of the galaxy, these differences add up, and the interstellar population becomes a mixed fleet. Some fragments dusty and lively, some crusted and quiet, some rocky, some icy, all shaped by their local histories before learning the wide road. There are rarer tales as well. A close brush with a giant planet can tidally stress a small body, flexing it, cracking it, changing its internal structure and spin state. A collision between two planetesimals can fling off slivers, fragments with odd shapes, elongated or flattened, that then tumble chaotically. A passage through a dense gas ring in the early disk can strip a surface clean, scouring it and leaving a fresh, reflective layer that behaves differently under sunlight. Each of these stories leaves subtle fingerprints, patterns in light curves, colors, the presence or absence of a coma. None alone will point back to a specific star, but together they map the menu of processes that populate the space between stars with wandering fragments. After ejection, the journey is long and mostly uneventful. Cosmic rays, high-energy particles accelerating through the galaxy, slowly alter surface chemistry. They break molecular bonds, create new compounds, build complex organic films that darken and redden the outermost layers. Micrometeoroid impacts, tiny grains moving at high relative speeds, sandblast the surface, pitting it and mixing the top layer. Temperatures stay low for eons, far from any star, preserving internal ices even as the outer millimeters harden into a protective shell. When such a body finally crosses paths with a new star, its response to warming, how quickly activity starts, how much dust it lofts, where jets produce measurable accelerations, reveals the balance between accessible ice and insulating crust. In that sense, every interstellar visitor is a time capsule, not only of the place where it formed, but of how it aged in the deep cold. For 3I Atlas, the safest, simplest origin story runs like this. It was born as one of many planetesimals in a distant protoplanetary disk, likely beyond that system's snow line, where water and other ices were stable. It was stirred by one or more giant planets, or by a binary companion, or by the crowded traffic of a young star cluster. Over many orbits, it gained energy through repeated gravitational encounters, until one day it crossed the threshold and left its birth star behind. It drifted through the galaxy for a very long time, perhaps millions of years, perhaps hundreds of millions, its surface slowly toughening under the constant rain of cosmic rays and the occasional micrometeoroid impact. Now, for a brief season, it passes a new sun, our sun. Whether it wakes into a faint haze of dust or stays nearly star-like, its behavior is a quiet letter from a place we cannot visit, stamped by the physics that shaped it and the gravitational game that sent it on its way. What does this mean for our understanding of planetary systems at large? The connection runs through debris and dynamics. Interstellar visitors like 3I Atlas are not isolated curiosities. They are part of a continuum that links debris disks, exoplanet architecture, and the process of planet formation itself. Debris disks, those wide rings of dust seen glowing in infrared light around other stars, are the visible cousins of interstellar fragments. They represent material that stayed, ground down by collisions into fine powder that slowly spirals inward or is blown away by stellar winds. High-resolution images of debris disks have revealed narrow rings, clumps, and gaps. structures that almost beg for unseen planets to explain them. Those patterns are the footprints of gravitational sculpting, of worlds nudging pebbles into resonances, sweeping some orbits clean while feeding others. A disk that shows strong structure today likely had a lively scattering past, a history of planetesimal stirring. Interstellar visitors are the long-distance consequences of that past, the pieces that found the exit rather than a stable niche. Ejection rates, the number of fragments thrown out per system per unit time, turn into a census question that feeds directly back into models of planet formation. If the rate is low, then visitors like 3I/Atlas are rare treasures, and the galaxy's interstellar population is sparse. If the rate is high, then the space between stars is quietly crowded with wandering shards, a slow, invisible rain that any star system passes through. Early estimates, based on the first two detections, ʻOumuamua and Borisov, left wide error bars as they should. Detecting even one interstellar object is a matter of luck, timing, and survey capability. Detecting three begins to narrow the range. As survey cadences sharpen, as instruments push deeper and faster, more visitors will be logged, and those error bars will tighten. The result will flow back into planet formation models, adjusting how often giants migrate, how strongly they stir, and how heavy the original disks must have been to produce the observed export. The connection to exoplanet systems is more than abstract. With thousands of exoplanets now catalogued, we have a statistical picture of planetary architectures. Some systems pack multiple planets into tight orbits close to their stars, configurations that suggest inward migration. Some have distant giant planets on wide, eccentric orbits, hints of violent scattering events. Some show debris disks with gaps and asymmetries that betray unseen companions. Each architecture implies a different efficiency for ejecting small bodies. A system with hot Jupiters, giant planets that migrated inward through the disk, likely flung enormous amounts of debris outward during that migration. A system with a distant, eccentric giant suggests past scattering events that could have ejected siblings. A system with no detected giants but a cold debris disk might be holding onto its rubble more gently, storing it rather than expelling it. By tallying the types of interstellar visitors we detect, their activity levels, colors, sizes, and speeds, we learn which family layouts produce which exports. If most arrivals look dusty and active, that leans toward icy origins beyond snow lines, fragments rich in volatile material. If many look inert and crusted, that suggests either longer exposure to cosmic rays and surface processing, or formation in warmer regions closer to their parent stars. If shapes tend to be irregular, that hints at collisional shards. If rotation states are unusual, that might trace back to tidal encounters during ejection. The patterns, once enough visitors are logged, become a map of planetary system demographics written in the debris they discard. Speed and direction add another layer. If the incoming velocities of interstellar objects cluster around the typical motions of nearby stars, that suggests a well-mixed population diffusing slowly through the galaxy over billions of years. If there are occasional fast movers, or objects arriving from unusual directions, that could hint at recent ejections from clusters or binary systems with higher ejection speeds. If the distribution of orbital inclinations looks isotropic, random on the sky, that confirms the objects are coming from all directions, not from any preferred plane tied to our solar system's structure. Each of these statistical properties, built up from many detections, constrains the unseen population and the processes that feed it. There is a feedback loop here, quiet but powerful. Planet formation theory predicts ejection rates and compositions based on assumptions about disk masses, giant planet migration, and scattering timescales. Observations of debris disks provide one test, showing which systems retain dust and which do not. Observations of interstellar visitors provide another test, showing what actually arrives at other stars. When the two agree, confidence grows. When they disagree, theorists go back to the drawing board, adjusting models to match reality. This is how science tightens its grip on truth, not through single dramatic revelations, but through slow, patient accumulation of constraints from multiple lines of evidence. For 3I Atlas specifically, its existence as the third confirmed visitor is itself a data point. It says that the rate is not vanishingly low. It says that modern surveys, given time and coverage, will continue to find these objects. It says that the galaxy's interstellar population is accessible to measurement, not a theoretical abstraction. And it hints, gently, that we are only beginning to sample the diversity that is out there. If 3 visitors show 3 different personalities, one enigmatic and tumbling, one familiar and dusty, one modest and tilted, then the population likely contains even more variety. Rocky shards, icy fluffballs, crusted husks, fresh fragments, all drifting through the dark, each one carrying a faint signature of the system that made it and the process that set it free. The future of interstellar visitor detection is brighter than it has ever been. New eyes are opening on the night, instruments designed to sweep faster, see deeper, and catch faint movers earlier in their passage through the inner solar system. 2 projects in particular stand out as game changers. One is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, currently under construction on a mountaintop in Chile. The other is NEO-Surveyor, a space-based infrared telescope designed to hunt for near-Earth objects, but perfectly suited to spotting faint interstellar travelers as well. Together, they represent a step change in capability, and they promise to turn the trickle of detections into a steady stream. The Rubin Observatory is built around a single, elegant idea. Photograph enormous swathes of the sky over and over again, night after night, season after season, for a decade. The field of view is huge, covering an area equivalent to 40 full moons in a single exposure. The camera is the largest ever built for astronomy, a 3.2 gigapixel monster capable of recording faint objects down to magnitude 24 or fainter. The cadence is steady, each patch of sky revisited every few nights, building up a time-lapse movie of the entire southern hemisphere and a good chunk of the northern. From pairs of images taken minutes apart, software can detect tiny motions, spotting asteroids, comets, and anything else that shifts against the background stars. From images taken nights or weeks apart, it can link those detections into tracks and calculate preliminary orbits. What makes Rubin transformative for interstellar objects is depth and speed. Depth means catching smaller, darker objects earlier, when they are still far from the sun and not yet racing away into the outer solar system, where they fade beyond reach. A visitor detected at 5 or 6 astronomical units gives months of lead time for follow-up, for spectroscopy, for coordinated photometry, for watching activity develop as it approaches perihelion. Speed, the rapid cadence, means linking dots into tracks before the trail grows cold. Many interstellar objects move quickly across the sky, and if you miss them in the first few nights, the uncertainty in their position grows large, making recovery difficult. Rubin's relentless rhythm reduces that risk. There is also the benefit of uniformity. Using the same telescope, the same filters, the same calibration pipeline night after night means that measurements from different epochs compare cleanly. Color changes, brightness variations, subtle trends in activity all become easier to detect and measure when the instrument and the method stay constant. This is the advantage of a dedicated survey over patchwork observations from many different facilities. The data speak the same language. Neo-surveyor takes a different approach, looking not at reflected sunlight, but at thermal emission, the faint infrared glow that even a cold, dark object radiates simply by virtue of having a temperature above absolute zero. Designed to hunt for near-Earth asteroids that might pose a threat, it will operate from a vantage point in space, away from the glare and absorption of Earth's atmosphere. By observing in two infrared bands, it can measure not just brightness but temperature, and from that, back out the true size of an object. This breaks the old ambiguity between large and dark versus small and shiny. A faint optical detection might be a big dark rock or a small icy snowball. Infrared measurements settle the question. The geometry is another superpower. Many near-Earth objects and some interstellar visitors approach from the sunward direction, the part of the sky where the sun sits. Ground-based telescopes avoid that region. The glare and scattered light make observations difficult or impossible. A space telescope designed for thermal wavelengths and built to tolerate sunward viewing can patrol that blind spot. Where optical surveys say later, an infrared mission can say now, catching objects while they are still inbound, before they swing past the sun and begin their outbound journey. Early detection transforms the science. It gives time to plan spectroscopy, to coordinate observatories across longitudes, to watch activity wake up rather than catching it on the decline. It allows rotation periods to be measured with confidence, colors to be sampled at favorable phase angles, and non-gravitational accelerations to be detected over long baselines. For faint interstellar visitors, which fade quickly as they move away from the sun, early detection can mean the difference between a rich dataset and a handful of marginal observations. What becomes easier with these upgrades? First, pre-perihelion discovery. The earlier a traveler is found, the more nights remain for detailed study. Rubin's depth and cadence will flag candidates months in advance, giving the global community time to mobilize. Neo-surveyor's infrared sensitivity will catch dark objects that optical surveys might miss entirely. Second, reliable orbits quickly. Dense observations from Rubin, combined with infrared positions from Neo-surveyor, will pin down paths with minimal uncertainty, allowing the hyperbolic signature to be confirmed or ruled out within days rather than weeks. Third, composition clues for the dimmest objects. Thermal measurements pair with optical colors to separate size from reflectivity, to watch how dust production changes with solar heating, to detect subtle variations that optical light alone cannot reveal. Cadence and coverage are the quiet heroes. Rubin's cadence, imaging the accessible sky every few nights, means very little slips through unnoticed. Its coverage, focusing on the ecliptic, but also sweeping high and low latitudes, finds motion at all angles, not just along the planet's highway. Neo-surveyor's coverage focuses on the sunward lanes, systematically scanning the bright directions where ground-based surveys are nearly blind. Together, they shrink the hiding places. An interstellar visitor, arriving from almost any direction, at almost any time, stands a good chance of being flagged. There is a social dimension as well. Alert systems, Software brokers that digest the nightly flood of detections will filter and tag moving objects, highlighting those with unusual speeds, colors, or preliminary orbits that hint at something interesting. Amateur and professional networks already practice rapid handoffs, and as the new systems come online, these handoffs will become smoother, faster, more efficient. The time from first detection to confirmed interstellar status could shrink from weeks to days, perhaps even hours in favorable cases. The upgrades also help when nothing dramatic happens. A clean, early non-detection in infrared sets a tight upper limit on size for a given optical brightness. A steady, geometry-driven brightening curve argues for a quiet, inactive surface. A flat phase angle response hints at coarse grains rather than fine dust. These are small, sturdy facts, constraints that narrow the space of possibilities. Even when an object refuses to perform, refuses to sprout a tail or show obvious gas emission, the measurements still teach. Will every interstellar object become a headline? No, and that is fine. Most will remain faint, telescopic targets known primarily to specialists, but the rate of discovery should climb. The fraction found before perihelion should grow. The diversity sampled should expand, and with enough entries in the ledger, patterns will emerge. Which surfaces wake easily? Which stay crusted? Which speeds and inclinations are common? Which are outliers? The answers to these questions feed back into the bigger picture of how planetary systems evolve, how much debris they eject, and what the galaxy looks like when you zoom in on the space between the stars. The instruments are being built, the pipelines are being tested, the global networks are ready, and the next visitor is already out there, drifting through the dark, waiting to cross our path and write another quiet line across the sky. 3 truths fit easily in the mind as the night deepens. First, interstellar is a geometric fact, not a mood or a mystery wrapped in conspiracy. A path with eccentricity greater than 1, a positive energy balance, an open hyperbola. These are not debatable interpretations. They are measurements, checked and rechecked, agreed upon by independent teams using different methods. 3i Atlas will not return. It is passing through once, and that single fact separates reality from speculation. The orbit does not lie. Second, faint is not empty. A dim point of light, a smudge at the threshold of detection, still carries structure, color, timing, and hidden forces. Measure brightness carefully over many nights, and it reveals rotation, hints at shape. Compare colors through filters, and the surface speaks, leaning red with age or neutral with coarser grains. Watch the path with astrometric precision, and tiny, non-gravitational nudges whisper about vents and jets too faint for cameras, but loud in the mathematics of motion. None of this requires spectacle. The quiet art of calibration, stacking, error bars, and patient accumulation turns whispers into sentences. Even absence is data, a lack of detected gas, a flat light curve, a null result on non-gravitational acceleration. These are not failures, they are constraints, fences that guide interpretation and keep speculation honest. Third, knowledge is a team sport played across time zones and disciplines. Surveys keep a tireless heartbeat, sweeping the sky night after night, building tracklets and flagging candidates. Follow-up telescopes sharpen the view, gathering spectra, colors, precise positions. Archives donate pre-discoveries, lengthening the timeline and tightening orbits. Careful mathematics ties the knots, fitting observations to models, propagating uncertainties, testing robustness. The work is communal, distributed, patient. One team flags a candidate, another confirms the motion, a third measures colours, a fourth stacks deep images and pulls a coma from noise. Together, piece by piece, the portrait emerges. The orbit settles, the safe distance hardens. The activity level finds its equilibrium, and the map of what matters stops shifting. This is not the science of dramatic revelations and midnight breakthroughs. It is the science of steady accumulation, of small wins shared until they become something larger than any single observation. The data travel through hands and servers, from dome to pipeline to plot, gathering context and confidence. And when the paper is written, when the results are published, the acknowledgements read like a star map of contributors, each one adding a sentence to the story. If a forward-looking thought belongs here, let it rest on the instruments waking up, the surveys gearing up, the networks tightening their coordination. Reuben will sweep deeper and faster. Any surveyor will feel the warmth of dark visitors hiding in the sun's glare. Together, they will turn rare chance into regular rhythm. The ledger of interstellar guests will lengthen from a curious shortlist to a statistically meaningful sample. Patterns will appear, not guessed but measured. Which surfaces are active? Which are crusted? Which inclinations dominate? Which speeds cluster? The picture of how other systems build and discard their rubble will sharpen from plausible models to tested science. There is comfort in how small the stakes are for us, and how large the meaning can be for knowledge. For Earth, 3I Atlas is a distant passerby, a wide berth confirmed by geometry and repeated observation. There is no danger, no tidal strangeness, no mysterious force reaching across the void. It is simply a small, cold fragment, following the mathematics of gravity on a single sweep past our star. For knowledge, though, it is a specimen, pulled by chance onto a lit stage for a single act. Its quietness is itself a clue. A modest coma, or none at all, tells of surfaces sealed by dust or depleted of volatiles, shaped under another sun and weathered in the long cold. A hint of colour, a flicker of rotation, a nudge in the orbit. Each is a thread connecting distant laboratories to unseen landscapes. Stories about the universe do not need exclamation marks to matter. A measured hello can teach more than a shouted alarm. Think of the naturalist counting moths by a porch light, watching the ordinary flutter, waiting for the wing pattern that has not been seen before. Nothing in the yard changes. Everything in the ledger does. Interstellar visitors are the cosmos offering exactly that. A chance to count, to compare, to learn what drifts between the lights. Allow one last image of scale and honesty to settle. The sun's gravity shapes a wide, smooth valley. 3I Atlas skims the contours, speeds where the slope is steep, slows as it climbs away. It never pretends to be anything but free. The path is open, the mathematics clear. Telescopes do not try to tether it. They simply watch, record, measure, and let the trajectory speak for itself. There is generosity in that restraint, and it is the same generosity that makes this kind of science restful. Truth without urgency, curiosity without alarm, attention given freely, rewarded with understanding. If a single closing thought should linger, let it be this pair. The universe is open, and attention is enough. Open because fragments born around other stars can cross the space between and pass through our neighborhood unannounced, obeying only gravity and carrying no allegiance. Enough because a careful eye, a patient instrument, and clean measurements can gather meaning from a faint line in the dark. The next visitor will come. There will be time to notice. The next survey sweep will flag a candidate, and a quiet alert will ripple across the globe. Another dot will shift against the grid of stars, and another story will arrive with it, written in motion and light. Let the breath slow. Let the thoughts settle like dust on a windowsill. A traveller from another star has passed, drawn a single silver thread through the dark, and moved on. The numbers are in. The geometry is clear. The distance is safe. The orbit does not close. And 3 truths fit back into the pocket where they belong, small stones to carry forward. Interstellar is geometry. Arrive and depart. Faint is full of information, if you know how to listen. Patience shared becomes knowledge, steady and kind. The rest can wait for morning. If sleep arrives now, it arrives on good terms, with a question floating like a lantern in the mind, gentle and unforced. What might the next quiet visitor teach when it crosses our sky only once? The answer will come in time, in data, in the patient work of instruments and people who watch the night. For now, the story is complete enough. The visitor has passed. The sky remains open, and the long watch continues, calm and untroubled, under the same stars. If this kind of science helps you find rest, a like and subscribe keeps Sleepy Science Drift easy to find, a harbour for calm curiosity and quiet wonder. Warm thanks to those already here, already part of this small community of night watchers and patient learners. If you feel like it, share in the comments where you are tonight, where this story found you, by a bedside lamp, on a late train, under a soft blanket, with the window cracked open to the cool air. Small notes make a quiet map of listeners scattered under the same sky, all holding the same question softly, all willing to let the answers arrive in their own time. The silver thread fades, the room settles, the familiar hush returns, that particular quiet of late night when the world outside has paused and the only sound is your own breathing, slow and steady. Sleep can come whenever it likes. The story is patient. It needs nothing more. A quiet visitor, a safe distance, a gentle bow to the sun, and a long road continuing through the dark beyond the window, into the space between stars, where other travellers drift, waiting for their turn to pass through the light.